Hello students, welcome to the next topic. So in the last topic we have seen how the maximum likelihood hypothesis related to the squared error, right? So how when you are trying to square the errors, right? So when you are looking into the least squared error hypothesis, how maximum likelihood hypothesis HML, that is the final equation, which is equal to argmin of di minus h of xi, that is observed data minus your hypothesis predictions h of xi. So we tried to establish that particular link in the previous section. Now in today's section we will be looking into the maximum likelihood hypothesis for predicting probabilities. So predicting probabilities means what? Now say for example, consider the setting in which we wish to learn a non-deterministic function f, right, or probabilistic function. Non-deterministic means what? So we are trying to consider an example wherein which you cannot determine what is the output. So we have got non-deterministic, we cannot determine. That's when you are unable to determine what will be the output, like say for example rolling a dice. So you can say that rolling a dice is non-deterministic. Why? Because you cannot predict what is the number you are going to get. It depends on the probability. You can only tell by giving some probabilities. So if we try to consider the examples wherein which we are talking about non-deterministic probability function f, so such that is function from x. What is x? Set of all data samples what you are having. So and what is the output? Is going to give either 0 or 1. So which has two discrete output value. So you are going to consider a non-deterministic function or probability function from x to two discrete output values 0 or 1. Now for example, now assume a particular database you are having, right? You are going to collect some details about the patient exhibiting based on certain symptoms. Now there are certain symptoms like say cold, headache, fever, body pain, etc. You consider certain particular, observe some of the symptoms for the patient. Then we might find that 92% survives. Suppose say that you are talking about, you are going to give an hypothesis which says that with this particular observable symptoms on set of the data points what you are having, what you are collected for various patients, the survival rate in a particular disease, right? You are talking about one particular disease. Now for that particular disease you have some symptoms and we are going to give a hypothesis. You are going to state an hypothesis. What is that hypothesis? Says that 92% of the patient survives from this particular cancer or a disease. Okay, any disease you can say, and 8% do not. So 8% is not going to survive or they die. So now you have some data. Now this is unpredictable, or what we can say non-deterministic. You cannot predict. So based on some data you are telling 92% survives. Now what about 8%? Now that 8% what you are telling, even though they suffer from the same symptoms, but still they are going to die. Actually speaking, with the same symptoms, with this whatever the same thing is there, or you can say like say for example, now when a doctor is going to do a surgery, or let us say is trying to do a heart surgeon, right? He is an expert heart surgeon. Now when we say that, now when he is conducting an operation or when he is going to operate a particular patient, 92% of the operation, or like say 98% is his success rate, right? So now and 2% is the failure rate. That means when he is going to conduct the operation, there is a chances, still it is unpredictable, even though the hypothesis is telling that 98% of all the patients on whom he has conducted the operation, now they have survived, but still there is a chances that some patient may die. So that is uncertain, right? So everything is uncertain. Now this unpredictability could arise from our inability to observe all the important distinguishable features of a patient. Now why this uncertainty comes is that even though you are going to have some parameters, based on that parameters you take the values, still we cannot, as a human being, it's very difficult for us to look into the all the or try to understand or try to differentiate some of the feature. That is why that unpredictability comes into the picture. Now if we are talking about these type of example, then how we are going to predict the probabilities. Now given this problem setting, now we might wish to learn a neural network or any other real valued function approximator. Now we want to learn, we want to have a real valued function approximator whose output is the probability that f of x is equal to 1. Probability that, see, 1 means what? Say 92%. So what we want that the patient is going to survive, right? So if a new data set comes, if you get an example or if you get a data set of another new patient, now we want to see that now what is the success rate, right? If he is going to survive, if 1 means he is going to survive, 0 means he is going to not survive. So based on all the characteristics or whatever the symptoms you have observed from this data, now we want to have such a type of a learning network. Now in other words, now we see that now to learn the target function, now you want to learn a target function f dash such that x to 0 comma 1, right? Two discrete outputs what you are going to have. So what is the percentage he is going to survive, whether that particular new patient goes into that classification or is not going to survive, which hypothesis, such that what is this target function f dash of x. Now f dash of x is equal to probability of f of x is equal to 1. Probability of saying that this patient comes or he survives, right? F of x is equal to 1. So now f dash, now this is what you are going to learn now. F dash of x should be equal to probability of f of x is equal to 1. Now in the above example, if we consider, now if x is one of those indistinguishable patient, now you have got one particular patient, right? So let us say you have a particular patient x, and we know that for every patient there are certain attributes, let us say a1, a2, a3, etc. Some attributes will be there, headache, body pain, etc., etc. And for all these things, now you are going to have an output, right? Output y, right? So if based on this particular symptom for this particular patient, it can be either 1 or 0. So 1 means what? He survives, 0 means he is not going to survive. Now if you take one particular instance x, so now what we are telling, 92% survives. So 92% survive means what is our f dash of x now? F dash of x is equal to probability of f of x equal to 1. Right? What is it? What when you say f of x equal to 1? 92%. So probability of this is how much? 0.92. So probability is 0.92, and when you are telling in percentage, it is 92%. So then we say our f dash of x is equal to 0.92, whereas the probabilistic function f of x will be equal to 1. In 92% of the cases, they survive, and equal to 0 when it is 0, remaining 8%. Remaining, if 92% is surviving, means obvious that 1 minus of that probability, 8% is going to, or the patient is going, patient are not surviving the cases. Now our question is, what criterion should we optimize in order to find a maximum likelihood hypothesis? Now what are the criteria we have to optimize so that we are going to get a maximum likelihood hypothesis for this f dash, right? So for this f dash, now how we are going to come up to that particular equation, we'll see. Now we must first obtain an expression for probability, that is posterior probability of d given h. For all the data set what you are having, what is your hypothesis? The survival rate 92%, what we are telling, right? This much percentage, a new patient comes, so whether that f of x is equal to 1 or whether f of x equal to 0, that hypothesis is there. So you are going to calculate, you have to get an expression for probability of d given h, and let us assume that the training data d is of the form, how is our training data? x1 comma d1 as we told. So here if you take this as x1, now with so many features are there, now what is the output? Output is d1, so you can say output as d1. Now this output d1, it can be either 1 or 0. Similarly, you will take another input x2 with so many parameters. Now you will be having an output. What is that output? We can call it as d2. Similarly, x3, d3, right? So now how is your training data? If you assume the training data D is of the form x1 comma d1 comma x2 comma d2, like that xm comma dm, where this small di is the observed 0 or 1 value for f of xi. Now it is very clear. Now for this f of xi, for now you are going to say here, now what is f of x1? So if you take here, what is f of x1? Now for this x1, for this data, you got d1, right? Now this d1 can be either 1 or 0. So what will be f of x1? It depends. If it is 1, so you are going to write f of x1 as 1, otherwise it will be 0. So where di is the observed 0 or 1, it can be either 0 or it can be 1 value for this f of xi. Now treating both xi and di as random variables, because we are talking of predicting probabilities. We are considering non-deterministic probabilities. We don't know what is going to happen. It is not deterministic. We can't tell correctly, right? Probability you have to give. Now if you consider these instances x1 data what you are going to collect, that xi is also random, and what output you are going to get, 1 or 0, whether he is going to survive or whether he is going to die, right? That also as random. So if you treat both xi and di as random variables and assume that each training example is drawn independently, already we have discussed, each training example is drawn independently, they are not dependent on each other, right? So tossing a coin, independent event, because second time when I am going to toss a coin, it does not depends on the previous time, you cannot tell, right? So your xi and di both are random variables, and assuming that each training example is drawn independently, then we can write p of d given h, the probability of d given h as, so now probability of d given h is equal to product. So why we are writing here product? Because we are talking about independent event. So when you are using this term independent event, now we will be talking about the product. Now it is equal to pi, or product of I is equal to 1 to m. So probability of xi, so probability of, that is p of xi for all the training examples, comma di. So what is the output you are going to get for this particular hypothesis? So this output for that particular hypothesis, whether it is 1 or 0. So we can write probability of the entire data set D given hypothesis is equal to product x1, x2, x3, x4, right? For all of these things, x1, x2, x3. So you are going to find, first take the first one x1, do the product. So you find the probability of x1 comma, what is this d1 for a given hypothesis, right? For a given h. So multiplied with x2, x3, etc. Like this you are going to do for all I is equal to 1 to m. Now, so what we got, probability of d given h is equal to pi I is equal to 1 to m, probability of xi comma di given h. Now it is reasonable to assume, further we can assume that the probability of encountering any particular instance xi is independent of the hypothesis h. As already we told that this xi what we are going to have the input data, now it is independent of the hypothesis. So it is completely independent of our hypothesis. Whatever the data set you are going to have, then you associate probability based on the given hypothesis, right? We can assume that. And when x is independent of h, so when this x is completely independent of h, it does not depend on this hypothesis h, now we can rewrite this expression as probability of d given h equal to pi of 1 I equal to 1 to m, probability of the same thing, this previous equation, xi comma di given h is equal to product of, for I is equal to 1 to m, probability of, we'll take this term first, probability of di given h comma xi multiplied with probability of xi. How we got this? This is by Bayes theorem. So you are going to apply your Bayes theorem. With the help of the Bayes theorem, we are going to write this. So probability of xi comma di given h can be written as probability of di given h comma xi into p of xi. Right? So let us consider this equation of 1, or as far as your textbook it is 6.8. Now let us assume this is our the first equation. Now what is the probability of di given h comma xi? That means if you take your first term here, probability of di given h. So now what is this probability of di given h comma xi of observing di equal to 1? What is the probability that it gives 1, right, for a single instance xi given a word in which hypothesis holds? If you are going to consider the hypothesis in your entire hypothesis world, what is the probability that this di is equal to 1, whether the patient is going to survive? Right? Now h is our hypothesis regarding the target function. So the hypothesis is related to this d, target function, whether 1 or 0. 1 means he is going to survive, otherwise he is not going to survive. Now which computes this very probability? So now therefore what we say that probability of di equal to 1. So we are going to look how much percentage he is going to survive. So probability of, instead of di, we can tell that di equal to 1 given h for xi is equal to h of xi. See, we are just looking into the hypothesis. Now what is our this hypothesis? Di output di equal to 1 means that is a hypothesis, 92%, how much percentage is going to survive. So directly now the probability of this di equal to 1 given h comma xi, it can be written as h of xi. I think it is very clear. Now it is the hypothesis for xi. When you take one instance or one example xi, now based on our hypothesis, what is that hypothesis? Whether this patient xi is going to survive. So if he is going to survive means output di will be equal to, what will be the output? Di will be equal to 1. That is what we are doing here. So probability of di equal to 1, right? So now we can say this as h of xi. So now we can rewrite this equation mathematically. We can still simplify this. Probability of di given h comma xi is equal to h of xi, right? Hypothesis for all the instance xi when if di equal to 1. When di equal to 1. If di equal to 0, then what will be the probability? It is 1 minus of this, 1 minus of h of xi. This is very basic from our probability. Suppose say that you are going to toss a coin, right? So you are going to toss a coin 10 times. Now what is the probability that you are going to get head? You are going to see. So first time you tossed a coin, let us say you got head. Second time you tossed a coin, you got tail. Third time you tossed, you got head. Like this you are going to toss 10 times and you try to note down. Now how many times you got head? Now let us say when you count here 1, 2 like this, suppose say that you got head 6 times. Out of 10 experiment, 6 times you got head. Now what is this? I can call this as P. One event, probability of getting head. Let me denote it as P. Now P is equal to how much? 6. 6 times you get head. Now if I ask a question, if you get 6 times head, how many times you have got tail here? You have tossed a coin 10 times only. 6 times if you get head, how many times you are going to get tail? If I indicate that as Q with a variable Q, probability of getting tail. Now what will be your Q? Q will be 1 minus of P. What is P? 6 times. So it will be 1 minus of that, right? So we can say that now if you are going to get 6 times head, then obviously 4 times it will be the tail. So you will be getting head 4 times, right? So 10 out of 10 experiment, 10 times when you are going to conduct, 6 times if you get head, obviously the 10 minus 6 is 4. So we say that P plus Q is equal to 1. So that is a standard equation, that is probability of getting head an event A and probability of an event B, when you are going to add, always it should be equal to 1. So here 1 is the, that is what the standard equation. Based on that probability equation, if h of xi, you are going to write probability of di given h comma xi is equal to h of xi. If d is equal to 1, then what will be if d is equal to 0? D is equal to 0 means 1 minus of this term. So you can write it as 1 minus of h of xi. Now that the same equation what we had, this complicated equation, now we have simplified it and mathematically we are writing like this. Clear? So now, in order to substitute this into our equation 6.8, or what we took this equation. So now this entire right hand side equation 1 or 6.8. Now we got this, right? So probability of di given h comma xi can be written in this particular form. So we will try to substitute that. So when you substitute that, what we are going to get equal to h of xi into di, right? H of xi to the power of di multiplied with 1 minus h of xi to the power of 1 minus di. So now how do we get this equation, right? Now you just take this particular equation, So now here we have di equal to 1 and di equal to 0, right? So now in this equation, if you substitute di is equal to 1, we are simplifying that equation. Now what will happen? This di is 1, right? So 1 minus 1 is 0. So 1 minus 1 0 means anything to power of 0 is 1. So now this entire term becomes 1. So what we are left with? We are left with only h of xi to the power of di. What is di? Di is 1. So h of xi to the power of 1 is h of xi. So we will get only what? H of xi. So what is this h of xi? Probability of di given h comma xi equal to h of xi when di is equal to 1. If you substitute di as 1. Now you go to your previous equation. When di is equal to 1, what is this? It is equal to h of xi. Same equation we got. We are just rewriting that equation. We are simplifying this equation, right? Now in this equation, if you put di, if you put di is equal to 0, now what will happen to the first term and second term? Now let us take first term, h of xi to the power of di. What is di? 0. So anything to power of 0 is 1. So this first term becomes 1 multiplied with the second term. Now in this second term, di is what? 0. 1 minus of 0 is 1. So 1 minus h of xi to the power of 1 is 1 minus h of xi. So when di is equal to 0, now we get same. Now you see 1 minus h of xi. Now this equation, in the next step, we are simplifying this. Mathematically, we are rewriting that equation in this particular form. Now, so we got probability of di given h comma xi. Now this entire RHS, now our equation 6.10 or equation 2, whatever you are going to call it, now we are going to substitute that in our previous. We are going to substitute that in this equation, right? So now we calculated this. Now we try to substitute this whatever we got here in that particular equation. So now what is that equation? It is telling probability of d given h. Now you see here, you see this. Probability of d given h is equal to summation of I is equal to 1 to m. Probability of di given h comma xi. Now this entire term we have rewritten it. So we have rewritten, this is what. Now we are going to substitute that here. So product of I is equal to 1 to m into h of xi to the power of di multiplied with 1 minus h of xi to the power of 1 minus di multiplied with p of xi. Clear? So we took that equation and this entire term probability we have substituted here, right? Now we can write an expression for maximum likelihood hypothesis, because now we calculated the posterior probability. probability of D given H with this equation. So now what will be your maximum likelihood? So H of ML equal to argmax. That is the standard, right? Already we have seen argmax of all hypotheses belonging to H. So probability of I equal to 1 to M, product of, so H of xi to the power of di multiplied with 1 minus H of xi to the power of 1 minus di into P of xi, right? So now when you consider this expression, now the last term is a constant. So now we have got the last term is a constant independent of H, so we can remove that. So what is that last term here? P of xi. Now if you look here, now this is for I is equal to 1 to M, and here argmax for hypothesis H. Now this is the probability of the instance xi. Nowhere you are associating with any hypothesis, so we can treat it as this term as a constant, and you can remove that term. So now once you remove that term, so your equation becomes H of ML equal to argmax of product of I equal to 1 to M, H of xi to the power of di into 1 minus H of xi to the power of 1 minus di. Now the expression on the right hand side of the equation can be seen as a generalization of binomial distribution. Now if you look this particular term, H of xi to di into 1 minus H of xi to the power of 1 minus di, this equation resembles our binomial distribution. So in our probabilities, we have different types of probabilities. One of the type of probabilities or one of the type of distribution is probability distribution is called as binomial distribution. It is very popular. Just like how we told normal distribution, we have got binomial distribution also. So it is the basics of a probability distribution. You can just Google it and try to understand the definition of a binomial distribution. Now when you look into the binomial distribution standard equation, now this resembles the binomial distribution. As soon as if you know that this is the equation of binomial distribution, if you have got an awareness or if you know that, so then easily you can say it belongs to binomial distribution. So as in the earlier case, since it is binomial distribution and the equation looks to be more complicated, now we will find it easier to work with log of the likelihood. Now we try to apply log to this so that it can be further simplified, because so this product, so whenever you have got a product, it is very difficult for us to calculate. So we convert it into summation. So how do you convert it into summation? By applying the logarithm. So now we apply logarithm to this. So HML equal to argmax H of small h of belonging to set of all hypotheses. Then this product term becomes the summation for I is equal to 1 to M. Now H of log. So you are going to apply log to. So we can say that. So again you have got a formula, very famous formula in logarithm. Logarithm of a to the power of x. If you apply log to a to the power of x, now this can be written as x into log a. X into log a. So with this formula we are going to apply. When you apply log to h of x to the power of di, so this becomes di into log of h of xi plus, right? So plus 1 minus, so again you are going to apply this log to this, so log to second term, so this becomes 1 minus of di into log of 1 minus h of xi. So we are applying the logarithm and you try to convert it into this particular equation. Now we see that now this is how. So when you try to maximize, now what we are trying, when you are looking into this particular expression, now it is very clear that now you are going to find the maximum likelihood. So you are going to find the maximum likelihood for your particular set of all data points xi. You have to see that either it is h of xi or it is 1 minus of xi, right? Either hypothesis is satisfied, that means the 1, right? Already we told, that means 92% is surviving, patient is surviving, either that or plus how many patients are not going to survive. So for certain set of all data points, now you got 92% as the success rate and 8% as the failure rate. For another data point you got 95% as the success rate and 5% as the failure. Another data point, you got 99% as the success rate, 1% failure. Now you are going to find maximum likelihood. Now out of these three, so which is argmax, right? Which is the maximum? So 99% success rate. So this is how now we can try to predict the probabilities. Now if you are going to consider a non-deterministic functions where you are unable to predict, where the function itself is non-deterministic, now in that cases this is how you can find the maximum likelihood. So we can find the maximum likelihood of our particular hypothesis, right? This is then another simple topic. Now this above expression, now it describes the quantity that must be maximized in order to obtain the maximum likelihood hypothesis in our problem setting. Now you can try to see which term has to be maximized, so that you are going to get the maximum likelihood hypothesis. Now this result is analogous to our earlier result, showing that if you look properly, the same thing what we have got, so which showing that minimizing the sum of squared error, right? Minimizing our sum of squared error produces the maximum likelihood hypothesis. So there, so when we have looked into the sum of squared error, so we went to the minimizing. Now that and this is almost same. So this is what now we are trying to understand. So now this is another simple topic what we have seen so in this particular session. Clear? So in the next topic, now we'll try to see, because so when we are talking about our maximum likelihood hypothesis or the maximum a posterior hypothesis, it looks very tedious or very lengthy for us. So to overcome this, now we'll see how best we can minimize this particular concepts, right? So or we can say that now we have talked of Occam's razor. So when you are talking about decision tree, so which decision tree we have to select? So we said we have got an Occam's razor, now which tells us that whichever decision tree is small, that is better for us. So like this, now here also when we are talking about hypothesis, now we will try to see the more in detail why or how we are going to come up with a minimum description hypothesis, so minimum length hypothesis. So those things we will be discussing in our next topic. So till that, so you try to read, because once again I'm telling, now in this particular topic lot of we can say the mathematics is been involved, all these equations. Only thing you have to understand it properly, try to read it properly twice or thrice, so then the concept becomes more and more simple for us. Clear? So if you have any doubt, you can ask the queries later, or you can try to contact me when you are coming to the college. So thank you. Have a nice day. Bye bye.